So far in this section, we've been considering partial derivatives for functions of exactly two variables. Well, we could have a function of more than two variables that we could have, say, g of x, y, and z. And in this case, we can think of three separate partial derivatives. We can think of the derivative of g with respect to x, the partial derivative of g with respect to x, partial g, partial y, or partial g, partial x. These three partial derivatives, oops, sorry, that should have been a z. Now I know my ABCs, gx, gy, and gz for that notation there. It works the same thing as, it works in the same exact way as it did earlier. If you want to calculate, say, the x partial derivative, fix y and z, that means treat as constants. And then take the derivative with respect to x. So let's just do a quick example here. So suppose f of x, y, z is x times sine of y plus 3z. In order to calculate out, let's say, the df dz, partial f partial z, the z partial derivative. Okay, so let's see here. X is a constant with respect to z. So we can leave that alone. The derivative of sine is cosine. Cosine of y plus 3z. But then we need to multiply by, using the chain rule, multiply by the derivative of the inside. But it's the derivative, it's the partial derivative with respect to z. Y is a constant with respect to z, so the derivative of this will be 0 plus 3 times 1. So the z partial derivative here is 3x cosine of y plus 3z. Okay, that was a kind of easy example. A slightly more involved example here. So this one is a physics application one. If you've done like certain electricity in terms of circuit analysis, you know, voltage, resistance, Ohm's law, stuff like that. And so something you should know here is that, and I should say, if this doesn't look familiar, that's a-okay. You can just treat this as given here. Let's say you have three resistors with resistances R1, R2, R3 in parallel. The equation that you get is 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. If these were in series instead of being parallel, you'd have a different equation. But we can think of this as, this is defining R implicitly in terms of R1, R2, and R3. So these three resistances we can think about. We could change R1 separately, we can change R2 separately, we can change R3 separately. And so in fact, I'm stealing this problem from the book because I think it's a good problem here. We're told find the partial derivative of R with respect to R2 when R1 is 30, R2 is 45, R3 is 90, and the units here are ohms. Okay, so what we want to do is, there's several different ways to approach this. I'm going to do a little bit different than what the book does. I'm going to rewrite this explicitly. R is 1 over all of this. R is 1 over 1 plus R1 plus 1 over R2 plus 1 over R3. And now we're going to take the partial derivative here. So the partial derivative of R with respect to R2. So let's see here. I'm just going to write this in this equivalent form, 1 over R1 plus 1 over R2 plus 1 over R3. So I'm going to use power rule instead of quotient rule. You get to the same place with them. Let's say, bring down the minus sign there, minus 1 times 1 over R1 plus 1 over R2 plus 1 over R3 to the negative second power. This is the power rule part of the calculation. And now we need to multiply by the derivative with respect to R2, the partial derivative with respect to R2 of the inside here. This is the chain rule part of the calculation. 1 over R1 plus 1 over R2 plus 1 over R3. And so this is going to be negative 1 over R1 plus 1 over R2 plus 1 over R3 to the negative second power. So the R2 partial derivative here of 1 over R1 is 0, because this doesn't depend on R2. 1 over R3 also doesn't depend on R2, so these give us 0. And then we're just left with the partial derivative of 1 over R2 with respect to R2, which will be negative R2 to the minus second power. Okay, so at this point then, let's just go to a new slide so we can get everything together here. Partial derivative R with respect to R2 ends up minus and minus, those cancel each other out. And so we would end up with R2 to the negative second power, 1 over R1 plus 1 over R2 plus 1 over R3 raised to the negative second power. So this is going to be 1 over R2 squared times all of this right in here. And realize that this whole thing, this was 1 over R. This is what we were originally given. So a more succinct way to write this is it's 1 over R to the negative second power. And so a really succinct way, 1 over R to the negative second power is just R squared over R2 squared. Okay, so now let's finish off the problem by plugging in everything. When R1 is equal to 30, R2 is equal to 45, and R3 is equal to 90. So this is going to equal, so our denominator here, R2 squared, will be 45 squared. But then the thing is, what goes upstairs here? So we know that 1 over R is 1 over R1 plus 1 over R2 plus 1 over R3. So let me plop in 30, 45, and 90. If you turn the wheels and crank all of this to solve for R, I'll skip the steps because it's just arithmetic at this point. You get 1 over 15. So 1 over R is 1 over 15, so R itself is equal to 15. So R squared is 15 squared, so we have 15 squared over 45 squared, which is 1/9. Let's just take a moment here at the end of this video to appreciate what the meaning of this partial derivative is here and evaluating at these three resistances. This basically means if you increase R2, then the corresponding overall resistance R will go up by about 1/9 as much. Or in other words, if R2 goes up by about 1 ohm, then R goes up by about 1/9 of an ohm. That's the meaning of this partial derivative here. Okay, I think hopefully those two examples should be instructive. Let me just point out here, this second example I think is particularly instructive just because it kind of shows that, you know, these partial derivatives are something that come up a lot in physics classes, especially, you know, in like the first year physics classes sequence and stuff like that.